Hi everyone, I'm Marc. Thanks very much for checking out this video. This work is about pattern counting problems in degenerate graphs, and it is joint work with Marco Bressan from the University of Milan. In this work, by pattern counting problems, I mean counting of subgraphs and induced subgraphs. So let me start with some notation and some background on those problems. For subgraphs, I will write in this talk sub from H to G for the set of all subgraphs of G that are isomorphic to H. I will most of the time call H the pattern, which we assume to be small, and G as the host graph, which we assume to be much larger. For example, if this is G and this is H, then those three subgraphs would be contained in this set. And I will write sharp sub from H to star as the function that, given a graph G, outputs the number of subgraphs in G that are isomorphic to H. We use the same notation for induced subgraphs, so I write in sub from H to G for the set of induced subgraphs of G that are isomorphic to H. Again, as an example, let this be G and this be H. And just to point that out, the first two are still induced subgraphs isomorphic to H, but the last one here, while it is a subgraph, it's not an induced subgraph, since those two edges here are not included. And again, I use the sharp notation here to depict the function that maps G to the number of induced subgraphs of G isomorphic to H. We are interested in the complexity of evaluating those functions. So given H and G, compute the number of subgraphs or induced subgraphs of G that are isomorphic to H. In the unrestricted setting, those problems are hard because, for example, both encode the k-clique counting problem. So for this reason, we can restrict the pattern graph H, and we usually restrict it in the following form, by restricting the class of allowed patterns. So formally, I consider the problems sharp sub from curly H and sharp in sub from curly H. And here we get as input a pattern in this class and an arbitrary graph G, the host. And then depending on whether we are in sub or in sub, we want to compute the number of subgraphs or induced subgraphs of G that are isomorphic to H. Just to make that clear, the class of graphs here is part of the problem definition and not part of the input. And then we ask for which classes curly H are those problems tractable. As I said before, if curly H would be the class of all complete graphs, then both problems would encode the counting clique problem, which is known to be hard. Now, by tractable, I actually mean fixed parameter tractable. So we usually consider, as I said before, the pattern to be much smaller than the host, and we formalize this by parameterizing the problem by the size of the pattern. And then we don't ask for polynomial time tractability, but as I said, for fixed parameter tractability. So more formally, our goal is to find out for which classes of graphs those problems are fixed parameter tractable, that is solvable in time f of the size of the pattern times the polynomial in the size of the host for some computable function. So even if f is, say, exponential, if the pattern is much smaller than the host, this is still counted as an efficient algorithm. Now, in this setting, those problems are already fully understood. So it is for subgraphs, a work of Kotechapian, Dell, and Marx proved that the problem is fixed parameter tractable whenever the class of allowed patterns has bounded matching number. Here, the matching number of a graph is the size of a maximum matching of a graph, and we say that a class has bounded matching number if there is an overall constant such that the matching number of each graph is bounded by this constant. They prove, if the class has bounded matching number, it's fixed parameter tractable, and in all other cases, they established hardness. Both sharp W1 hardness, where sharp W1 can be considered a parameterized counting equivalent of NP, but also a fine-grained lower bound under ETH, stating that there is no function f for which you can solve the problem in that time. Here m of h is the matching number of h. And up to this 1 over log factor in the exponent, this bound is actually tight. Then for induced subgraphs, similar classification is due to Chen, Tully, and Weyer, and again Kutikapi, Dell, and Marx. It is known that if the class of graphs is finite, then the problem is fixed parameter tractable. This is actually very easy to show, but the interesting part is that in all other cases, so for every infinite class of allowed patterns, the problem becomes hard, and still we get a hardness, we get sharp W1 hardness and an almost tight lower bound under ETH. And let me say here that for all natural classes natural classes H, we actually get a tight lower bound. Okay, so those problems have been fully understood, but if you take a look at the tractability cases, this is actually bad news. For example, in induced subgraphs, we can only hope for an efficient algorithm if the class of allowed patterns is finite. So we would like to get more, and now the idea is not only restricting the pattern, but also restricting the host graph. And this is what we did in this work. More precisely, we restricted ourselves to degenerate host graphs. So let me start with a recap of the definition of degeneracy. We say that a graph has degeneracy at most D if we can order the vertices of the graph in a total order, such that every vertex has at most D neighbors that are larger with respect to this order. For example, this graph here has degeneracy at most 3, because every vertex is adjacent to at most 3 vertices that are larger. And small degeneracy captures sparsity in real-world networks pretty well, which is the motivation for taking a look at degenerate graphs. Again, we are also not the first ones to study pattern counting in degenerate graphs. Let me give you an overview over some of the existing results. Now, the first one, more than 30 years ago, Shiba and Nishiseki proved that you can count k-cliques in linear time in D-degenerate graphs if the D is a constant. Much later, Bressan came up with an algorithm for counting homomorphisms from a graph H into a degenerate graph. And more precisely, he showed that the algorithm is efficient, that is fixed parameter tractable when parameterized by H and by D, whenever the so-called DAG tree width of the pattern is small. I don't have the time to talk about DAG tree width in detail in this talk, but we rely on it only in the black box matter. For those of you that know tree width, let me very quickly say that a DAG tree width is a modification of tree width that uses the degeneracy ordering of the degenerate host graph. Very roughly, that's the idea. Okay, and then last year and 2 years ago, independently from each other, Gishpolina, Levantsov, and Shapira, and Bera, Pajanasangi, and Sejatri established a crisp dichotomy for counting induced and non-induced subgraphs isomorphic to H in degenerate graphs. And their dichotomy classified the problem into linear time and nonlinear time cases, where the nonlinear time cases used an assumption from fine-grained complexity theory. In this work, we are also interested in counting induced and non-induced subgraphs, but our goal is to classify the problem into fixed parameter tractable and non-fixed parameter tractable cases. Now I can finally show you our main results. First, for subgraphs, we prove that given a k-vertex pattern graph H and a D-degenerate host graph G, we can count subgraphs in G isomorphic to H in time f of k and D, where f is some computable function, times the number of the vertices of the host graph to the induced matching number of the pattern times the log in the size of the host graph. Here, the induced matching number of a graph is the size of largest induced matching. For example, cliques and bicliques have induced matching number 1, but cycles and matchings can have arbitrary large induced matchings. And we complemented this algorithm with an almost tight lower bound. So we proved that whenever the class of allowed patterns has unbounded induced matching number, then there is no function f for which you can solve the problem at that time. So our lower bound in the exponent is asymptotically tight up to this factor of 1 over log of the induced matching number. And this shows that induced matching number, again up to this factor of 1 over log, is really the best exponent you can get in that setting, if you assume the exponential time hypothesis. For induced subgraphs, we proved a similar classification. So we showed that in case of counting induced subgraphs, we can do it in that time. And here the exponent is alpha of h, which is the independence number. And the independence number of a graph is the size of a maximum independent set of the graph. Again, for example, cliques have independence number 1, but bicliques, cycles, and matchings can have arbitrary large independence numbers. Similarly, as for subgraphs, we get an matching lower bound under the exponential time hypothesis, or at least almost matching. Again, we have this gap of log over alpha of h in the exponent. In both of our results, this 1 over log in the exponent is related to the problem of whether you can beat tree width, which is an open problem in parameterized complexity. If you resolve that problem, you might also close the gap, and then you get really tight lower bounds for our algorithms. Okay, so those classifications were like more stated in a more fine-grained form. But as promised, we also get an FPT versus sharp W1 hardness classification. So first, we call that in case we don't restrict the host graph and we parameterize only by the size of the pattern, then we have those classifications along the matching number and finiteness of the class of allowed patterns. And we prove that if you parameterize by the size of the pattern and by the degeneracy of the host graph, then we get fixed parameter tractability for subgraphs if and only if the induced matching number is bounded, and we get fixed parameter tractability for counting induced subgraphs if and only if the independence number is bounded. And then in all other cases, we can prove sharp W1 hardness. Now, let me spend the last part of the talk to give you some overview of our techniques. The most important ingredient for us was to express the number of subgraphs and induced subgraphs as a linear combination of homomorphisms. I will go into more details about that on the next slide. Having done that, we were able to get our upper bounds by using the algorithm for homomorphism counting over those stack tree decompositions due to Bressan. And we were able to get our lower bounds by applying the so-called complexity monotonicity principle and by a new construction, which we call F-gadgets, that allowed us to understand the homomorphism counting into degenerate graphs a bit better. Now, complexity monotonicity is a general framework that allows you to analyze the complexity of problems that can be written as such a linear combination. And I want to go in a bit more detail, present a bit more detail about those ideas. So I will use subgraphs as an example, but you can do the same for induced subgraphs. So yeah, as promised, we express the number of subgraphs, isomorphic to H, as a finite linear combination of homomorphism counts. And here, a homomorphism count, this term, sharp hom from F to star, is the function that maps a graph G to the number of homomorphisms from F to G. It is known that for every graph H, there exists such a combination, and the linear combination is actually unique. And then the complexity monotonicity principle states that evaluating such a linear combination is precisely as hard as evaluating its hardest term, with a non-zero coefficient. And that means if all terms here with the non-zero coefficients are easy to compute, then you can compute the entire sum efficiently. This is actually the easy direction. But then, surprisingly, the other way is also true. So if there is at least one term here with a non-zero coefficient that is hard to compute, then we immediately get hardness of the entire problem. And this property is really very special to linear combination of homomorphism counts. This property does not hold in general. Chen and Mengel and independently Kote-Carpendale and Marx proved this principle in the general setting. And then 2 years ago, Gishpolina, Levantsov, and Shapira observed that this principle actually remains true in the setting of degenerate graphs. And then equipped with those tools, we proved the following. We proved that if H has small induced matching number, then all graphs F with a non-zero coefficient will have small Deg tree width, which allowed us to use the algorithm for counting homomorphisms to degenerate graphs. And we proved that if H has a large induced matching number, then we will always find an F with a non-zero coefficient such that F contains as an induced subgraph the subdivision of a large expander graph. And this is a special case of those objects that I called F-gadgets on the last slide. And unfortunately, I don't have time for the details on that proof, but we were able to prove that whenever we have large F-gadgets in a graph, we can prove hardness of the homomorphism counting problem in degenerate graphs. And this then allowed us to get hardness of the entire sum by using the complexity monotonicity principle. Okay. So that was condensed on one slide, but feel free to ask me at the conference or write an email if you have any questions about details on this. I would, however, like to conclude this video with a particular open problem, which in my opinion is the most important open problem in this work. So we have classified subgraphs and induced subgraphs, but you might also wonder about homomorphisms. And similarly as for sub and in sub, I can write or I can define sharp hom from a class of graphs as the problem that expects a pattern in this class and a host G. And then the goal is to compute the number of homomorphisms from H to G. And this problem is fully classified in the setting where we only parameterize by the size of the pattern. It's known that it's FPT if and only if the tree width of the class of allowed patterns is bounded. And in our work, we also get results on this problem if we parameterize by the size of the pattern and the degeneracy of the host graph. And using the algorithm of Bressan, it follows immediately that the problem is fixed parameter tractable if the class of allowed patterns has bounded Deg tree width. And we were able to show that if the class has induced grid minors of unbounded size, then we get sharp W1 hardness. And here an induced minor is obtained by contracting edges and deleting vertices, but deleting edges is forbidden. And the question is whether this captures all classes already. So is there a gap between bounded Deg tree width and induced grid minors? And so our open problem would be the following. So either you can show that large Deg tree width already implies large induced grid minors. In that case, there is no gap, and we already have a complete classification for counting homomorphisms into degenerate graphs. Or there is a class of graphs that has unbounded Deg tree width, but only bounded induced grid minor size. And then we would be really interested to see such a class of graphs if it exists, and then analyze its complexity. Regardless, a solution of either one of those two points would significantly improve our understanding of counting homomorphisms into degenerate graphs. Okay, I'm out of time, so thank you very much for watching this video and see you at the conference. Bye.